All right, so in regard to the do now problems, we had said that the first one is sodium sulfide, binary ionic compound. The second one we said might be a little tricky. Copper is a transition element and it can form multiple cations, so you need to indicate which one. So your best approach here is to put the polyatomic ion in parentheses. If it doesn't have parentheses, that means you only have one of it, and the parentheses will help you with that. Nitrite has a 1 minus charge. 1 times 1 is 1, divided by 1 makes copper 1 plus. Have to be careful there. You'll see a few of those on your quiz, which for this class, period 3, is Tuesday. Copper, 1, nitrite. So for everyone who's on the band trip or out sick today, when you watch this video, you'll be all caught up. Alrighty, nickel 2 sulfite, what'd we get? Go ahead, Trey.
NiSO3.
Perfect. Ew. Go away. Good job. Aluminum phosphate, what'd we get? Volunteer, volunteer. Otherwise, I just pick you. I know some of you didn't get to it because you just came in from testing. Go ahead, Trey.
AlPO4.
Perfect. Where'd the 3 plus and 3 minus go? They canceled out. So aluminum, yep, 3 plus. Phosphate, PO4, 3 minus. The 3's drop down. You have 2 of the same number. They cancel 1 and 1. And if you have 1 of a polyatomic, you drop the parentheses. But you don't want to leave these charges here, which I think was your question, Ethan. Yeah.
No, I did phosphate instead of phosphate, so that's
Oh, okay. So if you did phosphate, you got AlPO3, because ite always has 1 less than 8. Okay, ammonium oxide. Go ahead, Ethan.
NH4 in parentheses with a 2 substitute, and then O2. I mean O, just O.
Just O.
Yeah.
Good job. All right. So hopefully naming and formula writing will be very straightforward. You have 2 quizzes in one on Tuesday. The first quiz is worth 100 points. It's naming and formula writing and writing electron configurations for ions, just like on classwork 2.1. Okay? The second part of the quiz is on oxidation numbers, and I'm going to teach you that today. And you'll have at least 35 minutes to practice in class. So by the time you walk out of here, you'll have a very high comfort level. You'll just need to do some additional practice on your own. If you don't have mastery of this concept yet, you'll get a little bit more of it today, but you really should be comfortable naming and writing chemical formulas for ionic compounds. Yes, Trey?
We don't have to know, like, copper, sulfate, and hydrogen.
You will in about 5 minutes, and it's really easy, okay? All right, so what we're going to pick up with today, I also really just want to take a couple minutes to show you a few tricks, because last time my focus really was on making sure you understood how to name and write chemical formulas for ionic compounds. And because I will give you the polyatomic ions on any assessment, you don't have to memorize them. But there are a few tricks that I think will be very helpful to you. So I would like to show them to you. When you get into an advanced chemistry, AP Chem, College Chem type course, they're not going to give you the polyatomics. You need to know them. And there are a few things we mentioned last time, but I just want to drive the point home so it's helpful to you. So one thing that we mentioned last time is when you have a polyatomic ion that contains O, it is called an oxyanion. It's going to have a negative charge and it contains oxygen. We had mentioned last time that the ite form has one less oxygen than the ate form, but you don't always have 3 oxygens in the ate. Sometimes, for example, sulfur, phosphorus, also with arsenic and manganese, you will have 4 oxygen for the ate form. But the ite form always has 1 less O than the ate form. So that's good to know. And that we mentioned with the do now, because I had asked for aluminum phosphate and you accidentally did phosphite. So I knew that you had an ending of PO3 instead of PO4. Not all, but a few elements in group 17 have the ability to make alternate types of oxyanions, not just ite and ate. So for example, the prefix hyper, or you can use per for short, means more than. Somebody who has hyperglycemia has high blood sugar. He or she is diabetic. A kid who is hyperactive cannot sit still. Too much energy. Last year you learned about hypertonic solutions, more concentrated than what was next to it. Yes, hypertonic from last year? Yes, yes? Okay, good. Hypo means less than. A kid who's hypoactive might be sitting there sleeping. Hypothermia means what? Low body temperature. Okay, you fall into a freezing cold lake, your body temperature may lower after a while if you're in there too long, although sometimes that helps preserve organ function. Somebody with hypoglycemia has low blood sugar. So hypo means less than. So for example, with chlorine, if you have 1 less oxygen than the ite form, 1 less, it is hypochlorite ion, and that's given to you on the back. If you have 1 more O than the ate form, then you have perchlorate ion. So hypo can only go with ite, 1 less than the ite form. Per can only go with ate, 1 more than the ate form. And you see that with iodine as well. And those are the only 2 examples I can think of. Also, if you had a sulfate ion, SO42 minus, if you linked a proton onto it, you would take away 1 negative charge. Actually, I take that back, not always. Yeah, always. So if you had, I'll go with the phosphate because that's what's given here. But if you had a phosphate ion and you linked a proton to this, H+, you'd take away 1 negative charge and you'd have monohydrogen phosphate ion. If you put 2 protons on, you'd take away another plus now, or you'd add a plus and you'd take away another negative, and you have dihydrogen phosphate ion. And again, these are also given to you on the back of the periodic table. So here we added 1 proton, we took away a negative. Here we added 2 protons, so we took away 2 negatives, if you will, and got down to 1 negative. You also can replace an O with an S. So if you had sulfate and you took away an O and put an S in, you get thiosulfate ion. And I mention that because that is a chemical that we use in the lab a lot. But there are tricks to the trade with the polyatomics. For this year, you don't have to memorize it, so don't get too bogged down in it. And truthfully, by the time you do a lot of naming and formula writing, you learn them without sitting there and just trying to pound them in your head. So by the end, you'll feel very comfortable with that. Okay, so we already did the naming and formula writing. I showed you the site if you wanted to practice, which I would recommend, and there was a cute iPad app as well. Where we're going to pick up is what Trey mentioned just a minute ago, This is on the hydrates, and this is very straightforward. Some ionic compounds have water incorporated into their structure. Their structure is known as a crystal lattice, and we'll talk about these at the end. But you can think about a crystal lattice, for example. When you were little, did you ever go climbing on those old-fashioned dome-shaped jungle gyms?
Yes.
Okay, now I don't know, I think I do know why, but you don't see them at the playgrounds anymore. I think because they were metal, they rusted out a lot, but I also think kids were falling off of them and breaking arms and ankles, so they got rid of them. But they were very fun. And if you took one dome shape going this way and you inverted it and you put another one on top, you'd almost have like a hollow soccer ball. And some ionic compounds have that type of structure. Now if you put water molecules in the middle, you have a hydrate. A hydrate is an ionic compound that has water molecules that are incorporated into the structure known as a crystal lattice. And we'll talk about these structures at the end of the chapter. Some of them pictorially are shown here. But again, we'll come back to the structure in a little more detail. It does get very complicated. The naming and formula writing of hydrates is very, very simple, and we're going to be doing a very cool lab on hydrates later in the year, where we're going to start with a hydrate, we're going to heat it up, and what happens is you drive all the water off of it, and you can determine the percent of water in your hydrate. And we'll do that probably in about 3 weeks, and it is a very fun lab. The kids like it. It works great. In terms of the naming and the formula writing, it's pretty straightforward. Barium chloride, you already know how to formula write. Hydrate means water, shown in red. And then before the word hydrate, there'll be a prefix. The prefixes are shown here. They are on the back of your periodic table, so there's no need to memorize them. Some of them you've seen before anyway. So look in the middle of your periodic table backside, and you'll see those hydrates just to the left of your subshell tree diagram. So for example, di means 2, like a diploid cell is 2N. 2 water. So when you do a hydrate, you write the chemical formula, you put a dot. It's usually not that big. I couldn't make it little on the screen. And then you have 2H2O. Calcium nitrate, you know how to formula right now. Tetra is 4. Hydrate is water. Pretty straightforward. Let's take a look here. If you heat this up, what you'll have left is barium chloride plus 2 water molecules. I'll explain that in much more detail when we do the lab. For now, we just want to name and formula write. So for example, strontium iodate trihydrate. Let's take a look at what we would have for this hydrate. What would strontium iodide be? And again, this is the formula writing for last time, and you should have mastery here. So strontium is 2+, iodate 1-, the 2 goes there, the 1 goes here. You put a dot. Tri is a prefix that means what? 3. And instead of hydrate, H2O. Who wants to help me with the next one? Go ahead.
Can I write it down first?
Sure, you want to say it out loud? I'll write it down too.
Okay, which is 3+.
Perfect.
bromine. It's BRO3 and minus.
Okay, and we had said the other day to put the polyatomics in parentheses. Okay, so don't forget. Go ahead, I'm with you.
And it's gonna be AL and BRO3 and then parentheses and 3.
Perfect. Now the dot, and it says tetrahydrate.
4H8.
You got it. Perfect. Excellent job. Alternatively, you can go the other way. For example, in this one, the following is given. And in this one, so let's try and name these. In the first one, Na represents sodium, and SO3 represents sulfite, and 9 is
Non-hydrate.
non-hydrate. Got a little squishy, sorry. I think this pen looks better. Alrighty, next up, Ian. Mg is magnesium. ClO3 is chlorate is correct. 8 is think about a sea creature that has 8 legs. What do we call it? Octa. And then what do we do? Not hydro, but hydrate. Good job. Easy peasy? Alright. Our main focus today is on oxidation numbers. In regard to oxidation numbers, as stated in your notes, these are numbers that are assigned to atoms that are by themselves, monatomic ions, atoms that are part of polyatomic ions, or atoms that are part of a compound. It's based on complete transfer of electrons, even though that doesn't occur. It's an assumption. You'll see that oxidation numbers can be negative, they can be positive, they can be 0, which you can see. They also can be fractions, which I don't think you'll see right now unless I did it for extra credit. Those get complicated. They're written plus or minus, then a number. So a charge, like calcium ion, has a 2+ charge. You'll see that for a calcium ion, the oxidation number is +2. So plus or minus, then the number for oxidation numbers. We're going to look at all the guidelines to assign oxidation numbers. There are a lot of rules. Initially, it may seem very overwhelming, but as we work through the problems, you'll be able to figure out what rule goes with what atom in an element, ion, polyatomic ion, or compound. The first one is that the oxidation number of a free element is 0. A free element is any element on the periodic table. So any element off the periodic table has an oxidation number of 0. So if I said calcium, you would tell me 0. Magnesium, oxidation number of 0. Lithium, 0. Aluminum, 0, etc. However, there are 7 elements on the periodic table that never occur by themselves. If they hook up with something else, you formula write as you learned the other day. You don't assume a 2. However, if you only have hydrogen and it's not linked to anything else, you never just have H, you always have H2. If you have bromine and it's not linked to anything else, you always have Br2. And each of these diatomic elements have an oxidation number of 0. It spells Brinkelhoff. It's easy to remember the 7, and you will need to learn the 7. They're going to come back again and again and again. There are some polyatomic elements where you have the same atom, but you have more than 2, and these have oxidation numbers of 0 as well. First rule. Second rule, if you have a monatomic ion, that is a single atom with a charge, so monatomic, one atom, charge making it an ion, the oxidation number is equal to the charge but written in oxidation number format. So calcium ion has a 2+ charge, oxidation number of +2. Lithium ion has a 1+ charge, oxidation number of +1. Sulfide ion has a 2- charge, oxidation number of -2. Tin 4 ion has a 4+ charge, oxidation number of +4. Free elements 0, monatomic ions equal to the charge. This one's a little tricky. It says the more electronegative element. We briefly talked about electronegativity in the previous chapter, and we'll talk more about it in the next chapter. Electronegativity is the ability of a bonded atom to draw electrons to itself. The trend across a period from left to right is that the electronegativity increases. Down a group it decreases, as we talked about in our periodic table chapter. In addition, on the back of your periodic table, you have electronegativity values for many, many, many elements. Hydrogen has an electronegativity of 2.2. The highest value is 4, so hydrogen's somewhere in the middle. Lithium, 1.0, so considerably lower than hydrogen. Beryllium. Nitrogen, 3.0. Oxygen, 3.4. Oxygen's the second highest electronegative element. The highest is fluorine. So fluorine's 4.0. In the example given, they mentioned NH3, which is ammonia. That's something that you clean with. It says the more electronegative element in a binary compound is assigned the number equal to the charge it would have if it were an ion. So when we look at the electronegativity values, nitrogen is 3.0 and hydrogen is 2.2 in regard to electronegativity, abbreviated EN. So what would be the higher electronegative, the more electronegative element, N or H? Which has a higher electronegativity, N or H? N. 3 is greater than 2.2. So if N were by itself and an ion, nitrogen's in group 15. What charge would a nitride ion have? 3-. So you figure out what's more electronegative, you figure out its charge, And that means that the oxidation number for nitrogen in ammonia is -3. In contrast, the other example says NO. We know the electronegativity of nitrogen is 3.0. What's the electronegativity value for oxygen? 3.4. So what's more electronegative? That would be oxygen. What ion does oxygen form when it's by itself? 2 minus, because it's in group. It's in group. Not too silly. It's in group 16. So if this has a 2 minus charge, what is oxygen's oxidation number? -2. And one thing you're going to learn in about 5 minutes is the sum, algebraically, the algebraic sum of the oxidation numbers, taking into account how many of each you have, will be equal to 0 for a compound. So if this is -2, what would the nitrogen be? Together they have to equal 0. +2. And nitrogen, like many elements on the periodic table, especially the transition elements and a lot of nonmetals, have the ability to have multiple oxidation numbers. And you'll see that in a few minutes. That to me is the hardest of all the rules. Okay. The oxidation number of hydrogen in a compound is typically +1. Oxidation number of hydrogen in a compound is typically +1. So for example, water, the H is +1. Hydrogen chloride, the H is +1. Ammonia, the H is +1. There is one instance where hydrogen is not +1. And that's if you have a hydride. A hydride is when you have a metal followed by hydrogen. So you're going to have a binary compound. It'll be a metal followed by hydrogen. Calcium hydride, the H is -1. Sodium hydride, the H is -1. Otherwise, hydrogen has what oxidation number, Ann? Kira, oxidation number of hydrogen in most cases is +1. Only when it's a hydride is it? So if you have a metal and then hydrogen, hydrogen has an oxidation number of -1. You got it. Now be careful. Why wasn't hydrogen -1 here? Is nitrogen a metal? No. Oxygen, typically -2 in a compound. There are a couple of exceptions. When it links to fluorine, it can be +2. It actually can be a lot of things. You really aren't going to see that, so we won't bother with that right now. Peroxides, such as hydrogen peroxide, sodium peroxide, the oxygen's -1. Oxygen is typically -2. For example, in water, oxygen's -2. Nitrogen monoxide, oxygen's -2. Carbon dioxide, oxygen's -2. Lithium carbonate, oxygen's -2. When it hooks up with fluorine, you get weirdness. I'm not going to go there. It's just too complicated. Watch the peroxides, though. Peroxides look funny. Remember that a peroxide ion, which is on the back of your periodic table, is as such. So if you have a peroxide ion, you will have O2. And also you'll see that it looks like it almost should be reduced, and it wasn't. So you usually can recognize a peroxide. Otherwise, oxygen, -2. And that's predominantly what you'll see. All right, we're almost there, and then all we have to do is show you how to do it and practice, 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 practice. A lot of practice. Group 1 and Group 2 ions, as well as aluminum ion, have oxidation numbers of +1 for Group 1, +2 for Group 2, +3 for aluminum. So sodium fluoride, lithium chloride, cesium oxide, the sodium, the lithium, the cesium are all +1. Calcium, the barium, the strontium, all +2. Anytime you have an aluminum containing compound, the aluminum's always +3. And here's the key. The algebraic sum of the oxidation numbers for all atoms in a compound, taking into account how many of each you have, is 0. Before we do that, I just want to take a minute to give you some examples of the rules we talked about, because I didn't give you examples of those in your classwork, so I want to make sure that you're golden here. So if I say to you, write the oxidation number for the underlined element for example, if I gave you selenium, what would the oxidation number for the element be? It's a free element. Oxidation number is 0. If I gave you the diatomic element hydrogen, what would be the oxidation number for the diatomic element hydrogen? 0. If I gave you the monatomic ion telluride ion, what would be the oxidation number? -2. You got it. If I said to you, I want to know the oxidation number for fluorine in the compound, look at rule E and tell me what the oxidation number would be for fluorine. -1. No, this is a little trickier. This is a binary, 2 different elements. Here you need electronegativity values. I'll tell you nitrogen's 3.0 and iodine is 2.7. So what would you do? Nitrogen's higher, so you'd figure out its charge. Right. Oxidation number -3. It's a little tricky. And then we can do 2 of these. All right, so in hydrogen fluoride, what is hydrogen typically? +1. When is it not +1? When there's a metal and then a hydrogen, and then hydrogen's -1. Now if you just have water, what is oxygen typically? -2. But if you have hydrogen peroxide, oxygen is -1. And we'll do more of that at the end. What I'm going to show you now is how to figure out the oxidation number for each, ooh, I'm sorry. I'll give you a minute to copy.
Number 6, because fluorine's like -1, why is it hydrogen?
I was just asking what hydrogen was.
So like if it was the whole, like,
If I asked you for fluorine here, it would have been -1. So I just asked you for 1. And that's exactly how I set up. You have like, I think it's 8 questions. And I would say probably 4 of them are from here. And then I did more, then I did what I'm going to show you next. But I didn't give you a lot of good examples of this on your classwork. I've already changed it around for next year, but that doesn't help you. But this basically is what I did, and I can give you more of these when I show you the big piece now, if it would be helpful to you. Okay. So now you've seen the rules, and with the rules in front of you, I think you can work through this, and ultimately you want to be able to put those rules away. But what we want to make sure that we can do now is figure out the oxidation number for each element in a compound using these rules and using some basic algebra skills. The first example shown says potassium permanganate, and you should have a high comfort level formula writing at this point. If not, that is something we want to address when we have classwork time at the end. So that's potassium permanganate. Now, typically, the element in the middle is the one that can have multiple oxidation numbers. So that's the one you're going to be looking for. To find it, you have to use your rules. For example, potassium in a compound. Potassium's in group 1. Its oxidation number is always +1. Oxygen typically has an oxidation number. Chris, the seat in front is open. If you can't see, you want to move up? All right. Oxygen typically has an oxidation number of -2 unless you have a peroxide. So far, so good? We're looking for the one in the middle. And here's where your basic algebra skills come into play. You have 1 potassium with a +1 oxidation number. So this is the number of Ks, and this is the oxidation number of K. We have 1 manganese, and that's what we're looking for. We have 4 oxygen, -2, and the algebraic sum for a compound is equal to 0. Basic algebra. 1 plus manganese -8 equals 0. Manganese -7 equals 0. Manganese is equal to +7. The oxidation number for manganese is +7. Manganese is a transition element. Like many transition elements, it has the ability to form multiple oxidation numbers. You also find that many of the nonmetals can form multiple oxidation numbers too. Sulfur does, nitrogen does, chlorine, iodine, phosphorus, etc. The math looks good? Basic baby math, right? Okay. There's another way to approach this. I do recommend it. If you only go after the polyatomic ion, which is the permanganate ion has a 1- charge, and you can get that off the back of the periodic table. If you find the oxidation number for an atom in a polyatomic ion, a compound is electrically neutral, so we set it equal to 0. A polyatomic ion has a charge, so we will set the algebraic sum equal to the charge. You'll get the same answer, it's just sometimes a little easier. We have 1 manganese, we have 4 oxygen at -2. We set it equal to -1 because that's the charge on the polyatomic ion. Manganese minus 8 is equal to -1. Manganese has a +7 oxidation number, and that sometimes will give you reassurance that you've done it correctly. You can do it whichever way you want. Sometimes it's easier to go after the polyatomic ion. I'll do several of them. Don't panic yet. On number 2, it says calcium oxalate, and again, you should have a high comfort level writing chemical formulas. If not, you didn't finish classwork 2-1 like you should have, and or you really didn't do anything extra to improve your understanding. You must be able to do this. Now on the oxidation number part of the quiz, I gave it to you like this, which may make it a little easier for you. Calcium in a compound. Calcium always has what oxidation number? +2 because it's in group 2. Very good. Oxygen typically has what oxidation number? -2 unless you have a peroxide. We're looking for carbon. Carbon can take on multiple oxidation numbers. We have 1 calcium. If I have 1 of something, I usually don't put a 1, like you wouldn't write 1x, you just write x. So we have +2 as the oxidation number of calcium, 2 carbon, 4 oxygen, set equal to 0. 2 plus 2 carbon minus 8 equals 0. 2 carbon minus 6 equals 0. 2 carbon equals 6, and carbon has an oxidation number of +3. You could go after the ion only if you wanted to. Oxalate ion has a 2- charge. So what would you set the algebraic sum equal to? Huh? Here in the permanganate ion, it had a 1- charge, so we set it equal to -1. Here we have a 2- charge, so what should we set the algebraic sum equal to?
-2.
That's correct. So you'd have 2 carbon plus 4 times -2 you'd set it equal to -2, 2 carbon minus 8 equals -2, 2 carbon is equal to 6, carbon's equal to +3. It's going to take about 4 examples or so, maybe 6 or 7. We'll do as many as you need. And then you're going to have about 35 to 40 minutes to just drive it home. Number 3 says aluminum sulfate. Raise your hand if you feel like you're getting a feel for this and want to do it with me. Go ahead, Robin. Oh, yes, sweetheart. You can do it. You can always phone a friend if you get in trouble. Aluminum has what oxidation number? You got it. I won't let you fall. Oxygen typically? You got it. How many aluminum do we have?
2, so it'd be 2 times 3 plus 1 s.
How many S's do you have?
3.
3. This goes back to counting atoms, chapter 2. 3 S's. Typically, we're looking for the one in the middle. It can have multiple oxidation numbers.
Plus 12 times -2.
And what do we set that equal to?
0.
Because it's a, starts with a C.
Cat.
No. C-O-M? Listen to your friends.
Compound.
Yes. Okay. Here comes the baby math. 6 plus 3s minus 24 equals 0. Oh, it is. Gotta make that an S. Silly, silly. Got it. Thank you. 3s minus 18 equals 0. 3s equals 18, and s is equal to plus 6. Yes, yes? Sulfur's kind of cool. It can go plus 6, it can go plus 4, it can go plus 2, it can go -2, it can do all kinds of fun stuff.
Will the element ever have an oxidation of a fraction?
It can. They're not common, but it can.
Uh,
I'll show you one separately after. I don't want to confuse the issue. All right. This is one where the math got a little bit heavier. Sometimes it is easier, you can see right here, to just go after the polyatomic. You have 1 sulfur, 4 oxygen at -2. What would we set that equal to? -2. S minus 8 equals -2, S is equal to plus 6. So you can approach it any way you want. And I'll give you an example where sometimes it is a little bit better to go after the polyatomic. The next one's really straightforward. Sodium perchlorate. Volunteer, volunteer. Otherwise I pick. All right, Amelia. Sodium, oxidation number? +1. Oxygen? You got it. Going after chlorine. How many sodium do we have? So just +1. 1 chlorine. How many O's? Times what? What do we set it equal to?
0.
Perfect. 1 plus chlorine minus 8 equals 0. Chlorine is equal to +7. Chlorine's kind of cool. Typically, the highest oxidation number doesn't go higher than the number of valence electrons for the nonmetals. Chlorine can be +7, +5, +3, +1, -1, can be all kinds of fun stuff. That one I don't think is really worth going after the anion because it was so easy. But the next set are where sometimes it's very helpful. 5 says lead 4 phosphate. So the first thing you have to do is you have to formula write lead 4 phosphate. And when you get subscripts down here and you get into substantial number of atoms, that's when I think it is easier to go after the anion. We'll do it both ways. Now they told you this compound was lead 4 phosphate. So what would be the oxidation number for lead here? 4, because the charge is 4 plus, so it'd be +4. If you had lead 2 phosphate, then the lead would be +2. Oxygen typically -2. We're going after the phosphorus. We'll do it both ways. 3 times +4 plus 4 times phosphorus plus 16 times -2 is equal to 0. 12 plus 4p minus 32 equals 0. 4p is equal to 20, and p is equal to +5. Okay? It might have been easier to go after the polyatomic anion directly. I told you. Can't see back there. Just don't block out the little girls behind you. Okay. Here you just have the 1 phosphorus, the 4 O's, and what do you set that equal to? -3. P minus 8 equals -3. P is equal to +5. It's actually easier, is it not? Yeah. All right. 6 is tricky wicky. This goes back to what we talked about in the do now activity. What's the charge on the copper in this ionic compound?
Would it be +1?
It would be. Very good. It would be, the charge would be 1 plus, because remember what we said earlier, this is 1 minus, therefore that's 1 plus. So because this is copper 1 nitrate, copper has a 1 plus charge, what would the oxidation number on copper be? +1. And if you went about this wrong, you'd get the nitrogen wrong, and that's why the check is always a good idea. So you'd have 1 copper at +1, 1 nitrogen, 3 O's at -2, set equal to 0, and N would be equal to +5 for the N in a nitrate. If you went after it in the nitrate ion alone, I think you would find it easier, and in addition, you would make sure that you calculated it properly, because if you anticipate incorrectly on the copper, or I shouldn't say anticipate, I guess determine, then you're going to mess up your N2. So be careful there. One more, and then I'll give you more little problems if you want, but I'd like you to take a break then, and also you'll have a solid 35 to 40 minutes to do your classwork. Number 7 is much harder than anything you will see on your quiz, except maybe if you take a makeup. I think I put one of these on a makeup. Ugh. When N hooks with H, N is -3. Hydrogen is always +1 unless you have a hydride, and you don't. Oxygen's -2. You're looking for the sulfur. I'm going to let you try that one. In number 8, you've got lithium acetate. I'm going to give you some hints here. Again, these are much harder than what you're going to see on your quiz. But if you really, really, really want to make sure you can do anything, you should try these 2, and you can try 9 as well. Before you do try these, your goal today is to make sure you understand oxidation numbers. It fits in with our overarching learning goal that we've been talking about for the past week. Your quiz will be on naming, formula writing, electron config of ions with isoelectronic atoms, and oxidation numbers. I can give you an example of a sample type oxidation number quiz toward the end of the period, and we can write all that out very slowly if you want to. Try and finish these up. I'm going to cut the video here, and then we'll address any and all concerns that you may have.